Good afternoon, everybody, and welcome to May's edition of Standard Motor Products Pro Training PowerHour. This edition, Engine Operation, keeping everything in time. I'm Wayne Bishop, and I'll be your host. We have a lot to cover, so let's get started. All right, folks, today's class will basically focus on cam and crankshaft synchronization. The control module needs precise information where the moving parts are. Now, we understand that PCM has to control the fuel system and the ignition system, but modern cars also have variable valve timing as well, mechanical timing as well. We'll start with cam and crank synchronization and see how all these interact with each other, all the moving parts, keeping it in time. All right, folks, let's get started. Like I mentioned earlier, the PCM needs precision position sensing. This little video I'm showing right here shows the piston going up and down. You can see the little animation. There's a fuel injector injecting at the right time. Also, the spark plug ignites the fuel at the right time. At the bottom of the screen, you'll see a train, a pulse width train go by. Those are cam and crankshaft position sensors. It's more important than ever the PCM has precision position information in order to initiate the fire and the fuel at the right time. Now, speaking of the ignition system, we don't have room for error. As this slide illustrates, it's important to ignite the air and fuel at the precise time. That's only a few degrees of crankshaft rotation to get maximum power to ignite the air and fuel and push the piston down with sufficient force. Now, not to forgive my diesel guys, this is an example of compression ignition, diesel ignition. Diesel engines obviously don't have a spark plug. They take tremendous amounts of air and compress it. That compressing the air makes tremendous heat. But of course, the PCM has to initiate the diesel fuel injection at the right time and end it at the right time in order for the diesel engine to have maximum power and minimum emissions. If you remember from our diesel after-treatment classes, some manufacturers actually inject diesel fuel post-combustion to get diesel fuel in the catalytic converter to initiate regeneration. So like I mentioned, we'll focus mainly on cam and crankshaft position sensors. And they're kind of interchangeable. So I'll basically call these 2-wire and 3-wire position sensors. All right, let's begin with 2-wire position sensors. In this slide, I have an illustration of a cutaway view of a 2-wire variable reluctance analog sensor. Some of you may call these AC pulse generators. The term reluctance actually deals with the ability of lines of flux to permeate through a material. So just as resistance is resistance to current flow in an electrical circuit, reluctance deals with magnetic lines of flux. Now in this example, you can plainly see here in the middle, they're simply a permanent magnet. Very simple, very robust, a good old get-her-done sensor right here. That magnet has coils of wires around it. And we know from our training that electromagnetic lines of flux can force current flow through a conductor. So the way this thing works is when that magnetic lines of flux come in contact with the pole piece right here of the reluctor, the lines of flux want to extend away from there. And they do it very uniquely. The lines of flux come out, they want to grab this piece of magnet, and of course that causes current flow in one particular direction. Now the other side of this, the reverse of this is when the hole comes around like this, those lines of flux, of course, collapse back. And in doing so, they cause current to flow in the opposite direction, 180 degrees. That's where you get the classic AC pulse from. Current flows one way or the other, positive, negative. Like I said, it's a very simple, it just works, but it's not perfect, it's not bulletproof, it has flaws. See, notice over here I got some talking points right here. Some factors that determine the health of an AC pulse generator: rotational speed. The faster the reluctor goes by, the more amplitude I have. Now, when I say amplitude of the signal, what I'm referring to again is this. The two ends of the frequency, if you will. That's the amplitude. The more amplitude I have, the more signal that my computer can actually see. So amplitude is good. So the faster it goes by, the more amplitude I get. Magnetic strength, now it seems pretty self-evident. You say, well, the stronger the magnet is, the more magnetic lines of flux you have, and the stronger my field is. That's true, but here's a problem with that. Permanent magnets aren't necessarily permanent. And you know how these sensors are all mounted in cylinder heads and engine blocks. What happens is heat over time degrades the magnet. So almost always, when these sensors fail, it's because heat actually degrades the magnet. The magnet fails and I can't produce a signal. Now, coil inductance is just a fancy term for the quality of the windings, the quantity and the quality of the windings themselves. So it makes sense the more wires I have, the more output I can get, but it's only to a certain point. After a while, you can only package so many wires in a sensor, okay? So the last thing I have is sensor air gap. Now you see this little air gap that's illustrated in this picture here? It's pretty doggone tight. And it is true. The closer the magnet is to the ferrous metal, the stronger the magnetic lines of flux extend out and the more amplitude I can get. And guys, sometimes just rust and corrosion, even these things are bolted in, most of them are got a plastic housing, just the rust or corrosion can actually hydraulic these things away and increase that by ever so slightly, but it's enough to make them fail. So let's look inside the computer. Let's look at the big picture right here. So I have an AC pulse generator, and notice I have a reluctor wheel right here beside it, and it's got 6 notches cut 60 degrees apart, and 6 times 6 is 36, and it kind of divides into 360 real good. But I also want you to notice there's a missing tooth or an extra tooth, whatever you want to call it, right here. You'll see tonight I have a couple examples where they'll have some unique feature. Now on a crankshaft position sensor, I'm just looking at 360 degrees to go round and round and round and round. But if I see the same waveform consistently going around and around and around, the computer doesn't have anything really to sync onto or to sink its teeth into. So you'll always find one unique feature right there the PCM can use to start counting from. Now also notice I have this 2-wire sensor hooked into a control module, and I show a chipset. Even though this thing's pretty good about producing a good solid AC pulse, it's an analog pulse. Computers don't really like analog food, they'd rather have digital food. So if I take this one step further, let's look inside the module. If we check the wires, which we'll check the wires on 2-wire and 3-wire sensors here in a minute, but understand there may be a bias voltage on there. A lot of us just assume, it's just an AC pulse generator, so there's probably nothing on the wires. But modern chipsets probably put a bias. Now I got an example that could be 1.5 volts, it could be 2.6 volts. Now the example I'm showing you in a few slides will be a GM product, a GM 4.2 liter to be exact. And GM puts a 2.6 volt bias on the wires. What they do is they'll elevate the ground off ground to have a nice clean bias to elevate the AC pulse, if you will. So if I check one of these, now I'm going to focus on the right-hand side of the screen, obviously over here. I'll use the same slide in a minute for the 3-wire sensor. But you see the PCM has 2 wires coming out, and there's actually a voltage tap and a little resistor right here, so you know there's power being applied right here. Now in the first example, I'll take my lab scope and I'll reference to earth ground, and I'm using 2 voltage probes. Now this is something most guys wouldn't do. I'm using channel A and channel B for a 2-wire AC pulse generator. But I got a good, decent, clean waveform right here to show you the example I'm talking about. 2.6 volts on the blue trace. And over here, notice my Pico, my 2.6 red's on the other side. But that looks like ground as far as the computer is concerned. So I elevate ground off earth chassis ground, probably because it's dirty ground, it's noisy ground. I lift it up, but that's okay. You'll notice I still have a pretty clean AC pulse. Also notice right here where I'm circling my laser beam, that's the double pulse. Remember, the computer needs something to sink its teeth into, and that's that unique feature right there. Now, I'm going to do this the other way. Now, I know this particular screenshot is noisy. There's a lot of things going on here. It's this Pico 7. There's hardly any room to even work with this, but I want to show you the same thing on the same lab scope, okay? There's 2.6 volts. There's 2.6 volts. Now, let me take my magnifying glass, and I'll zoom in here so you can see it better. That goes from about 0 to about 6 volts. So you see that's a decent little AC pulse, and the computer can probably see that all day long, all right? Now what I want to do is do the same thing, only different. Now I'm using the same scope, I want you to see the same picture twice. What I'm using now is I'm taking my lab scope, I'm using my positive and negative lead and putting it across both terminals. Now this is the way most technicians have been brought up to test an AC pulse generator. Is take the black lead and the red lead, let's just say, and put it across both wires. Now, doing so, I want you to notice something kind of special going on here. Do you notice now, where my little hand is moving around right here, you'll see that the 0 is now really on ground, but notice the amplitude this thing is giving me right here. That's 6 volts on the positive side, 6 volts on the negative side, for a grand total of about a 12-volt swing right there. I mean, that is a pretty good little sensor right there. I'm not saying there's any wrong way to do this or any right way to do this, but be aware there could be a bias voltage on the line itself. Modern technicians need to make sure the wires are good before we condemn parts, and then be aware of what you're doing when you test these. All right, before I move on to a 3-wire sensor, let's look at a 2-wire sensor on the bench. I'll show you how to test it with a meter. All right, folks, I moved over here to the bench, and I have one of our 2-wire AC pulse generators. Obviously, I said 2-wire. You can see it's got 2 wires on there. This is a classic Ford crankshaft position sensor. And notice how you can actually see the steel piece in the middle. This is a pretty strong magnet, and that little bar right there, you kind of amplifies what I was talking about. I got a crankshaft or a camshaft phaser right here. It's got a big hardy piece of steel, and that really is a decent magnetic pull right there. In fact, this thing can support its own weight if I wasn't dragging it down with this DVOM right here. So big strong magnet, and basically I've mentioned there's just a coil of wire around here. Now what I've got is my ohm meter set up right here, and we can still see it. What I'm gonna do is ohm it out. And you can see it's got about 300 ohms resistance, which you can imagine was about right. It's just a bunch of wire. Where this comes in handy is you want to test the integrity from point A to point B. Now it's one thing to test it right here within 6 inches of the sensor, but let's say you were checking, from the PCM to the crankshaft position sensor because you lost CKP. You can ohm this thing out, you can ring the wires out, and even if you had multiple connectors, you can see through them all and make sure you have a circuit back to it. So understand the manufacturer may give you a spec on this, and they're not always going to be 300 ohms. They'll probably give you a range because heat greatly determines the resistance of materials. Usually the hotter things get, the higher the resistance gets. So they may say between 200 and 400 ohms or something like that, or 200 to 500 ohms. But it gives you something to start with. Doesn't mean it's really good, but it's a starting point. Now just for Mr. Wizard right here, since I got my meter hooked up, I'm simply going to switch over to change it over from DC to AC volts. The point I want to make is this is a magic sensor. Remember I told you how simplistic it was, how bulletproof it was, how rudimentary, it's been around for 50 years. There's nothing going to it. It's just wire and magnets. But remember I got this reluctor right here. See the piece, see how it's got a unique signature right there? The sensor sits in close proximity and it goes around and around and around. And what I want to try to do, I'm not too good at this, but I want you to see my meter. You can actually see I'm producing voltage. If I could really get good at this, I would make a decent amount of juice right here. But the idea I want to show you guys is it really does make electricity. All right, let's get back to the presentation. All right, folks, let's look at 3-wire sensors. All right, once again, I have an artist illustration of a cutaway view with 3-wire sensor. Immediately, you can see there's more going on here. There's some commonality, but there's also some new parts involved here. Let's examine. The first thing in my eye sees, I can't help it, I like magnets, so I see a magnet right there in the middle. Yes, there's still a magnet in there, but I don't have the lines, the coil, the inductor that I had in an AC pulse generator. I need the magnetic lines of flux simply to excite this Hall effect chip. Now, these sensors always have to have an external power supply going to them. That's the dead giveaway. They're a 3-wire sensor. They'll have power, ground, and signal. The power needs to power up the chipset. So what will happen in this situation right here, a magnet being a magnet can't help itself, when that doggone reluctor wheel comes by, a ferrous metal comes by, the magnet wants to reach out and grab it. But instead of inducing current flow through an inductor, I simply make the Hall chip conduct. Now the Hall chip will conduct electricity, and yes, it will make an AC pulse right here because that's the nature of the beast right there. But what I'll use is these positive pulses, if you will, simply to turn on this transistor. Now the beauty of this, I can turn on off like a switch. And what I'll get is a clean digital square wave. Now the advantage of this is computers like digital food. I do not have to process an analog to digital processor. I simply have digital in, and the computer thanks me very much for that. I can process the information better. These sensors are more robust in the fact they're not so sensitive to slow reluctor speeds. They're a faster sensor, and they're also can be used at higher RPMs. And the beauty of these, they have a nice clean on-off transition. So let's look at the wires on the other side of this. Now notice I'm showing you the computer side. Now we looked previously at the chipset inside the camshaft position sensor itself, but again we're going to check the wires. Now I mentioned that we have ground, ground, ground. I got 5 volts in this case right here. Now they're not always 5 volts, folks. You might see a lot of Asian cars will typically put 12-volt power supply on it. That's okay. Remember, don't condemn sensors unless you know they're powered up first, okay? So I got power and ground, but notice this is kind of tricky. My signal wire is actually attached to a 5-volt pull-up circuit. That means the module supplies 5 volts to the signal circuit at all times. And if you remember from the previous slide, I showed you a transistor. That transistor's job is to take that 5 volts and switch it down to 0. So if I can add a little bit of scope right here, I guarantee you if I looked at that line, I'd see 5 volts. So there's 5 volts coming out. But it has the reluctor wheel comes around, the tooth comes around, and of course this sensor gets happy and it sees what's going on. It's going to take that 5 volts and simply pull it down or drop it to 0 volts. But again, the end result is a nice, clean square wave. Also, just for the heck of it, notice right here I do have that unique feature. All rotating reluctors have something to make them unique. So again, this is a crankshaft position sensor and it's got to have something the computer can count with. All right, so let's check the wires one more time. If I was looking at this and I was poking wires, now remember, theoretically I've unplugged the sensor and I'm front probing the connector itself and I'm pinning these little tiny wires. Yes, I should have ground. The 5E should say, you can imagine that, 5E, but what confuses a lot of technicians, and I used to be one of these myself, it blew my mind. If I took a meter and put it on a signal wire, I always thought a signal wire was just a wire waiting on something to happen. But in reality, that's a 5-volt pull-up. I will read 5 volts. And remember, the chipset pulls it down. All right, let's look at further testing. Now, again, in this example right here, I've got my scope set up again. Now remember, we just checked the power supply. Now notice this example here, I'm showing a 12-volt. That's okay. They need an external power supply. I've checked my ground, and the only thing left is really to check the signal. Now, when you have a 3-wire sensor, really the best way to look at these, honestly, is with the lab scope. Because you'll validate the signal's integrity, but you can also validate even the reluctor's integrity, because you'll see the pieces go by. These sensors are so precise, they'll paint an electronic picture of the reluctor itself, and we'll see that coming up in just a minute. All right, folks, let's finish up here and talk a little bit about variable valve timing. Now, talk about complexity. That is a typical modern engine. In fact, that's a 3.6 liter GM you're looking at. In fact, if you've seen them in our PTS classes all the time, it's our little favorite motor to work on, right? That's got 5 moving parts. There's a crankshaft and there's 4 camshafts. Each one has to be precisely monitored. And we'll talk about this in just a minute, but these camshafts can independently articulate, which is typical of most modern cars. So we'll have camshafts turning in different directions. What this does, it phases the camshafts and actually improves airflow dynamics of the cylinder head. I get the best of all worlds. I can have smooth idle quality, which we need, but also as I enter into mid-range torque, I increase the airflow through the engine. I can actually achieve better economy by decreasing pumping losses. Of course, I can also get emission gains by getting the EGR effect. And if I need to, when I really hammer down on this old girl, I can actually increase the compression by advancing the intake and get more zoom out of this engine. There's no downside to this. It really is the best of all worlds. But of course, it adds another layer of complexity with diagnosis. So understand that VVT is highly monitored by the PCM. In fact, if VVT errors can code because, of course, it can cause emission failures. When you troubleshoot these, please understand the DTC. There's performance codes, there's correlation codes, there's circuit codes, there's mechanical issues with the phasers and the solenoids, but there's also electrical codes that go with all the sensors. I mean, for heaven's sakes, there's 5 position sensors in here. Now, this adds complexity if you decide, well, I need to scope this thing, because now you have 5 moving parts. So it'll take your scoping skills to the next level. Let's look at how this works. In this slide right here, we'll talk about most intake camshafts are always parked at their most advanced position. And when they phase, they advance. So actually, the PCM not only has to understand where camshaft position is, but now it has to understand exactly which way is it going. Is it going clockwise or counterclockwise? Is it advancing in time or is it retarding in time? So as this chart right here illustrates, this is a waveform, pardon me, not a waveform, but the cam lift profile of exhaust cam and intake camshaft in operation. So notice in here in this zero baseline cam timing scheme right here, I'm moving my cam timing 30 degrees advanced. I physically moved it one way. And then the exhaust cams are generally parked at their most advanced position, and the PCM feels a need to retard those. So it really does go the other way in time. So it goes backwards in time. So the same illustration right here on this zero-based time guide right here, what you'll notice is the exhaust cam moves the other direction. It phases in the other way. So again, the PCM has another level of complexity. Now, the beauty of these things is modern computers are smarter, they're faster. They have more computing power. I mean, think about just most guys have probably had 3 or 4 phones in their lives now, and just understand how much computing power just your cell phone has. Automotive computers are also increasing in their computing power as well. So there's chipsets and algorithms that can define the cam no problem. Now, we're about to move on to our last little bit of the class right here, but I want to show you what looking at a good cam crank waveform looks like. In this example, you see the cam is in blue, the crankshaft is in blue and the cam is in red. But I want to make sure you see, if you do this, if you go through the trouble doing this, guys, make sure to get at least 720 crankshaft degrees. Remember, the crankshaft turns twice to one camshaft. So what I want you to notice, there's a missing tooth or a wide gap. There's some unique feature somewhere in the crank profile. From here to here is 360 degrees, but from here to here is another 360 degrees for a grand total of 720 degrees, right? Well, if the crank turned twice, this guy moved one time. So if you're going to bother to do this, make sure you at least see the entire camshaft profile, because you may have an issue with a bent reluctor or a missing tooth or a cracked tooth or something like that. If you're going to do this, make sure you see at least one good whole rotation, or at least make a movie of it where you can go frame by frame by frame and look at all the pieces. All right, folks, a few more things before we wrap up. I want to talk a little bit about how to connect our lab scope, how to probe the wires, how to check for cam and crank correlation. I even have a car behind me that will do this live in just a second. All right, remember, stick with service information. You got 3 wires on a 3-wire sensor, obviously. Identify the power, the ground, and the signal, and validate there is power, ground going to the sensor itself before you condemn the sensor itself. Remember, these things are highly monitored by the computer. There's probably DTC in there. Think about what you're doing. We talk about this in class all the time. Electrical things are generally straightforward. Mechanical things are difficult, but electrical, straightforward. There's generally circuit codes and performance codes. So think about what it's telling you. Generally, a circuit code means I don't have my power, I don't have my ground, I have a short, I have it open, I have a bad part. Those are generally easy for technicians to wrap their head around. Performance code means I might be working, but I'm working outside my parameters. And those are more difficult to wrap your head around because maybe you don't know exactly what the parameters are. So remember, when you hook up, and especially you guys who use your lab scope, generally speaking, most cars have known goods. There's 2 banks, there's 4 cylinders, there's 4 fuel injectors or 6 fuel injectors, whatever the case may be. You generally have known good parts. And then if you do have to actually test these, consider access. So here's what I mean by access. Here's an example of a 5.0 Ford pickup truck, and there's the camshaft position sensors, and that picture you're looking at, if you guys got a keen eye, you're saying, Wayne, that looks like a flywheel to me right there. It is. So in real life, that's a devil to get to. So if you can't get to the sensor itself, of course, the next best place is the PCM. Now, a lot of us shy away from probing the PCM, and yes, I'll admit it's not easy. You got to remove the hard shell, you got to probably pull the little wire stiffener inside of there, and then you probably have like 400 wires, and there may be some numbers on there that may not. Service information may be upside down, backwards, or a mirror image of those numbers, and if you're like me, you can barely see any doggone way. So I think this is a case where everybody probably has a magnifying glass in their toolbox, but use care. But anyway, here's this very same pickup truck, and the technician who did this saved a waveform for us. Now what you're seeing on this F-150 is the camshaft sensors at the bottom, and there's a crankshaft at top. Now notice how the crankshaft has one unique feature right there. That's the classic Ford missing tooth, but it makes a unique feature that you can easily see on the lab scope. And even this late model Ford still has an AC pulse generator for the camshaft position sensor. Now the car I'm about to work on here behind us, this little 200 Chrysler right here, I had to actually go to the camshaft sensor itself, and then for the crankshaft I chose to use a PCM. So here's a waveform I got last night. Here's a static picture of it, but we'll go live in just a second. As a matter of fact, let's go to the car live now. Let me just make my way over here to the car now. All right, folks, what I have here is a 2015 Chrysler 200, and you have to admit it's a pretty color of blue. That's about the only thing good I can say about it. What I've done right here with my lab scope is I have attached my probe. Notice my camshaft position sensor, which is camshaft number 2 on this car, was easy to get to, so I simply chose a back probe pin. I have my gator clip right there, but I located the signal wire. The crankshaft position sensor, of course, is way down here at the bottom, a little bit harder to get to. So as much as I hate doing this, it was actually easier to go to the PCM connector and finding that one wire. Remember, PCM connector views are sometimes very confusing because they're upside down, backwards, or sometimes even mirror images. So in all seriousness, be on your game, and if nothing else, that's why they make magnifying glasses. Please identify the numbers on the connectors, find the white wire. Sometimes, not always, but sometimes the color code works perfectly fine, so you identify simply what color the wire is. I've got my Pico hooked up with 2 channels. We'll crank this car up. I'll go back to my laptop, and we'll turn the Pico on live. All right, folks, I've got the car running, and I'm making way back to the laptop. Now what I'm going to do is switch things out here, so give me just a second to make sure everything works.
Now, if you start here, just say, all right, that's what we're going to run it down a little while.
All right, I got it running now. You notice it took me a second to boot Pico up. Let me turn on both my channels. I'll move the red guy over here a little bit. Now, this is not really a scope class, but I know some of you guys are scopies, so I got to at least tell you what I'm doing here. I know in my heart it's probably a 5-volt sensor, so I chose a 10-volt scale right here, and this allows me enough real estate on Pico that I can at least show both waveforms at the same time. I've chosen a time setting that lets me get a pretty good view of the pulse train going by my screen from one side to the other, and I can see both the waveforms on the screen. Now, the variable is the engine's RPM. It cranks up at a high idle, and as we talk, it's actually slowing down a little bit, hence my waveform is starting to change a little bit. But remember, I can always freeze this whenever I need to, and I can examine the attributes. If I want to look a little closer in this, I'm going to cheat because I'm a Pico guy. I can't help myself. But you can go in there and look and see a little bit better at the individual. Whoops, I don't want to see that. Anyway, I can freeze the waveform and actually look at, if I need to, any detail, individual pieces of the waveform if I need to. So with that, we'll turn that joker off. We don't have an exhaust pipe in our studio here, but y'all need to know that. What I've done is I saved the waveform from that Chrysler 2.4 liter. If I go to that much trouble, I at least want to save that waveform and build my known good database. Sometimes performance issues or correlation issues are sometimes compared to known goods. And having known goods on hand is actually a good thing. So if you do all that work, please, please, please save your waveforms, annotate your waveforms, make notes for them, and build yourself a database. And in closing, I cannot help but to mention, don't forget your doggone wires. I mentioned wires 2 or 3 times tonight: testing wires, poking wires, voltage wires, ohms wires, volts wires, wires. Don't forget your wires. The pins themselves are so tiny, guys, you can't fix anything. Sure, you might put contact enhancement on there, but these wires live in a bad environment. Sometimes they're completely oil soaked. The ozone, the hydrocarbons, the heat, the cold, they're a mess. Sometimes sensors fail, not because the sensor's bad, because the connector's bad. So replace the connector, replace the doggone sensor, worry-free repair. Now before we go, don't forget to check out Standard Brand's YouTube channel for additional resources like installation videos, quick tips, and additional product knowledge. And for more digital resources, check out standardbrand.com, where you can find tons of information around different product categories like cam and crankshaft position sensors, VVT, fuel injection ignition systems, and even ADAS. You can also access our ECAT and illustrated guide. And don't forget to register for next month's Power Hour. On June 12th, we'll discuss GM's 2.7 liter active fuel management, operation, and diagnosis. Hope to see you there as well. All right, before we wrap this up, I want to ask Corey, is there any questions out there?
So, yes, Wayne, we actually had several come through, quite a few come through, and I've been trying to answer as many of them in the back end here as I can in the spirit of time. However, there were 2 questions that came through that we had multiple. We had multiple people asking the same question. So I figured I would wait till we get to the end here so we can get that answer to everybody at the same time. And the first question is, do I always need to replace the cam and crank sensor at the same time? Can I get away with just doing one on some vehicles and not the others, or should I just do it on all of them, I guess is the question.
All right, Corey, that's a fair question. Well, the short answer is you can do what you want. You're free to repair the car as needed. But I'll be honest with you guys, when a camshaft or crankshaft position sensor fails, it's generally due to the high heat stress and the thermal cycling that it's gone endured. Usually one sensor is just as stressful as the other sensor is right there. So actually it's best to go ahead and replace them all while you're in there. You replace the package, if you will. In fact, some cars are so problematic, take our friends at Nissan for example, they actually have kits where they all come in one box. You get pigtails and you get connectors, or the pigtails and the sensors themselves are that bad. Now nobody's going to get rich selling cam and crankshaft position sensors. We do this to ensure the durability of the repair and get the car out of the shop and get it past warranty. So by all means, yes, I think you should always replace sensors in stereo. Put them in there. Anything else, Corey?
Yeah, I had another one this one we had 4 different people ask the question, so I figure if 4 are asking, everybody's going to want to know the answer to it. Mm-hmm. So we're talking about pigtails earlier. You were talking about that about halfway through the presentation, talking about pigtails. The questions that are coming through are similar here, and they're all around the same thing. So say I have an oil leak, and the oil leak gets into the pigtail,
sure,
and it destroys the pigtail. Obviously, I have to replace the pigtail, but can I get away with just the pigtail, or do I need to do the cam and or crank sensor, whichever one it is, at the same time? Is that going to be okay if I just reuse that old sensor, or do I have to do them both?
I hear you, Corey. Guys, what I would do is you have to think about the big picture. If oil's actually destroyed its connector, and these are actually built pretty durable, they're high heat resistance plastics, you have to always understand it's probably also permeated the sensor itself. What happens when oil passes these pins inside here, it gets down inside the chipset, and it may be working now, and you might even sprayed some carb cleaner there to clean it up or something like that. But honestly, if you're that far into it, so bad that the pigtail had to be replaced, refurbished, go ahead and put a sensor in there too. Again, you're doing the peanut butter and jelly right here. You're making the complete repair. You're done. See you later. The car's fixed. And for us, the best thing about the repair is it doesn't come back for the same problem. So I would say yes, by all means, replace both of them.
All right, Wayne. Well, that's pretty much all I have here. Mm-hmm. And I just want to thank everybody for joining us today. I want to thank you for being here. And again, with the spirit of time, I know we're a little bit over already, so I'm going to let you close us out and say thanks again, everyone, and have a wonderful day.
All right, awesome. Guys, thanks for coming with us this afternoon. I appreciate you visiting with us. This is my 19th year with Standard Motor Products, and I'm generally out and about doing live classes, but things are changing. I'm doing some virtual stuff. In fact, I'm here in Dallas this week, and it was probably a happy accident I was here anyway. So I want to thank you guys for seeing us live. I thank you for tuning in virtually, and folks, I'll see you next time. Thank you very much.